All right, the Diels Alder reaction. It's a reaction of a 1,3 diene, a conjugated diene with an alkene or an alkyne. We call the alkene that gets reacted or the alkyne that gets reacted a dienophile. Uh, ophile means it's something that is liked, and so a dienophile is something that likes conjugated dienes. And the reaction looks like this. You take a 1,3 conjugated diene, you add a carbon double bonded molecule or triple bonded molecule. The pi bond breaks and attacks this carbon, which causes this pi bond to break and form a pi bond here, and then this pi bond breaks and forms a single bond with this carbon. So all you have to do is take a conjugated diene with an alkene, add heat, and you get this molecule here, simply a cyclohexene. All right. Conjugated diene plus an alkene and heat gives us a cyclohexene. Just takes a little bit of heat, forms a six-membered ring. 3 pi bonds are broken. 1 pi bond and 2 sigma bonds are formed. This pi bond gets broken, this pi bond gets broken, this pi bond gets broken. We form a new pi bond here and a single bond between these two carbons and those two carbons. All right. And all bonds are broken and the new bonds are formed in a single step. This is just one step. All breaking and bond making happens at the same time. Okay. Let's look at the reactivity, though. The diene must be in the S-cis conformation. But recall, the S-cis, kind of looks like this. Kind of the two pi, looks like this. The two pi bonds are cis to each other, if we were to draw a line there. But recall, with S-trans and S-cis, you can rotate S-trans to the S-cis as long as there's not some sort of ring connecting them. So you can rotate the S-trans to the S-cis, get it in the S-cis conformation. And it turns out there are other molecules that are held in the S-cis conformation. Look at this one right here, this cyclopentadiene. Here you've got the single bond, or double bond, single bond, double bond. In the S-cis configuration, they're held together by that ring, so this will undergo Diels Alder. Note here you have a conjugated system, double bond, double bond, but due to these two rings, these are going to be held S-trans. Make the model, you will see that you cannot take this bond and rotate it. This single bond here cannot be rotated in this molecule. The ring structure is holding it in place. So this will not undergo Diels Alder reactions because it's in the S-trans configuration, and Diels Alder requires S-cis. Okay. Let's look at the reactivity of the dienophile, the double or triple bond. It turns out electron withdrawing groups on that dienophile increase the reaction rate. Halogens, oxygens, especially carbonyls. So if you look at this double bond right here, and if we had an aldehyde or an ester here, or this molecule here, maleic anhydride, this double bond is going to be more reactive than just a normal double bond. So if we look at this double bond here, it'll undergo Diels Alder reactions, but these guys will do it better. These will do it faster, make more product. These are just better at doing Diels Alder reaction because they are electron withdrawing. Also, if you have electron donating groups, by the way, electron withdrawing, electron donating, we're going to get to that in the next chapter. What groups do that? It turns out methyl groups are electron donating. So the best Diels Alder reactions have electron withdrawing groups on the dienophile and electron donating groups on the diene. Methyl groups and alkyl groups on the diene, oxygen containing groups on the dienophile. That being the case, this looks to be the opposite. There's no electron donating groups here, but we've got two CH3s, two methyl groups on this. The Diels Alder reaction will still happen here. It's still a good reaction that works really well. It's just this dienophile right here, the double bond, is not as reactive as these double bonds down here. All right. And now you're thinking, oh, that's really cool, but what about stereochemistry? Yeah, well, it turns out this is syn addition. Because the reaction happens all in one step, as this double bond is breaking, note this, the COOH, these two carboxylic acid groups are cis to each other on this double bond. They will remain cis to each other in the product, because as this double bond is breaking, the single bond cannot rotate, because as that double bond is breaking, these single bonds between this carbon and this carbon and this carbon of the CH of the dienophile of the double bond is reacting with this carbon here, forming a bond here. So this single bond that's forming never gets a chance to rotate, because as it's starting to form, as the double pi bond is breaking, these two single bonds are forming and the ring locks it into place. So if these two COOHs start out cis to each other, they're going to end up cis to each other also. And note, that gives us a chiral carbon right here. Here's a chiral carbon. We've got the coming off of it 4 different groups, a COOH, an H, the ring this way, and the ring that way, and it's different going around the rings. So this is a chiral carbon. We generated a second chiral carbon here. But note, there is a line of symmetry. The top half of the molecule is the mirror image of the bottom half of the molecule. Therefore, this is a meso compound, and it is not optically active. It doesn't have its enantiomer, because if you were to draw the mirror image of the molecule, you'll find out the mirror image of the molecule would be the same as just taking this molecule and rotating it 180 degrees over. Take this molecule, rotate it 180 degrees, you get the mirror image molecule. So it has no enantiomer. Its enantiomer is itself in this example. Okay. Well, now let's look at this situation. Let's have our diene here, and our dienophile. Note the two groups are trans. If you add heat, you'll get this reaction to occur. Diels Alder, gotta love it. You make a cyclohexene. And so now this COOH group will be going back, and this one will be coming out. If they start trans, they have to end trans, which means we've got a hydrogen here, both 2 chiral carbons, 1 chiral carbon right here, 1 chiral carbon right down here. But note, it's not a meso compound. So this is an optically active molecule. It will have its mirror image, and that mirror image is non-superimposable, so we have the enantiomers. Recall from Organic 1, there are 2 ways to draw the enantiomer, 2 ways to draw the mirror image of a molecule. One way is to actually just draw the mirror image, just kind of make the mirror image, pretend there's a mirror here and draw the mirror image. The other way is to switch 2 groups on all of the chiral carbons. Here we have 2 chiral carbons here. So if I switch the H and the COOH on the top one, make the H be going back and the COH coming out, change the mirror image of the top, or change 2 groups on the top carbon. Do the same on the bottom. For the bottom carbon, have the H coming out and the COOH going back. So I've switched 2 groups on both the top carbon and the bottom carbon. On both chiral carbons, I now know this is the enantiomer, the mirror image of that. Okay. And if you do the models, or if you can see it in your head, if you took this molecule right here and rotated 180 degrees like this, it was like this, rotated 180 degrees like this, you would see, oh, it is the mirror image. If I just rotate it, I can visually see the 2 are mirror images of each other. So, let's emphasize that point again. To draw the enantiomer of a molecule, switch 2 groups on all of the chiral carbons. What would have happened if we would have switched 2 groups on just 1 chiral carbon? What if we'd have switched the bottom 2, made this COH go back and this H come out, but left the top the same? Well, then those 2 would have been diastereomers of each other. Question, can we get the diastereomers here? No, we can't. Why can't we get the diastereomers here? Why is it that we only get these 2 enantiomers but no diastereomers? Because recall from good old Organic 1 again, if you have 2 chiral carbons, you have 2 to the n, good old 2 to the n. possible stereoisomers. And so 2 chiral carbons, 2 squared is 4. There's 4 possible stereoisomers, but we only get these 2 enantiomers because this single bond never forms until the ring is forming at the same time. These two are going to be held trans to each other. Therefore, they have to be trans to each other in the product. If you note, if you were to just change one group, just change the bottom group, these two COHs would be going back. Both of them going back. They'd be cis to each other, and that just can't happen. If they start out trans, they have to stay trans in this Diels Alder reaction. Okay, so what if we take this conjugated diene and add this guy right here? It looks kind of crazy, but yeah, it will work. You just say, okay, here's my double bond, just change the orientation a little bit, put the double bond here, and we get this system. It's a meso compound, and it's a bicyclic. We've got a ring here and a ring here. Okay. There are molecules that you think might not do Diels Alder. It looks like you have steric hindrance problems, and you do have some steric hindrance, but good news, it's not a problem. Let's look at Endo versus Exo Edition. If you have a bridged ring system, meaning you start with this cyclopentadiene, this conjugated double bond, single bond, double bond, single bond, single bond in this 5-membered ring, it will still react with ethene here and do a Diels Alder product. It's just the ethene will form a bond between this carbon and this carbon, and will form a bond between this carbon of the ethene and this carbon of the ring. You'll still make a cyclohexene. I don't know if you can see it, but this is the product. Cyclohexene starts carbon 1, 2, 3, 4, 5, 6. So if I labeled these carbons, and it's always a good idea to keep track, if I label, say, this is carbon 1, this is carbon 2, this is carbon 3, 4, 5, 6, call this carbon 7 up here, we can see that with our conjugated diene here, this is carbon 1. Note, we always form the double bond between carbons 2 and 3. It was always a single bond in our reactant. Now it's a double bond. It's 1, 2, 3, 4. 5 and 6 are these two carbons here, and 7 is that carbon of the ring. So this carbon of the cyclopentadiene ring ends up being what we call the bridging carbon. It bridges one side of the cyclohexane to the other side of the cyclohexene ring, excuse me. All right. But this reaction happens here, both CH2s here. What happens if we have another group on our diene? Take our same cyclopentadiene and make sure that this molecule isn't just CH2s for both of these. You would see that we could get Z down here, or we could get Z up here. You can use your molecular model, see all the different ways these can come together. When the groups are going down, if we look at our bridge here, remember, the bridge carbon is always the apex carbon here, or the CH2 carbon of this cyclopentadiene. We see this Z is going down away from that bridge. Here the Z is kind of next to the bridge. It's up next to the bridge. When it's going down, we call it the endo product, and that's the preferred product. When the Z is here, kind of on the same side as the bridge, as this bridging carbon, we call it the exo product, and due to steric hindrance, these two can be a little close to each other, so the endo product is always the preferred product. Okay. So, note, let's take our cyclopentadiene now and react it with this, what was this, maleic anhydride. Draw the endo and the exo products. Well, the endo product, this group here, here's our diene. It will be going right here. The double bond between these two carbons becomes a single bond, and those are the two carbons right here and here. And this is the endo product with the rest of this group, the carbonyls and this oxygen going down. The exo product has those guys going up. I cannot emphasize enough, get a molecular model kit, build these so you can see what they look like. You can see, okay, there is a little steric hindrance here. There is none here. Note that the endo product is always going to be the major product. If you would put methyl groups on this carbon here, start with 2 methyls here, the reaction will still work, and you get way more endo than exo product. All right. Cool. Let's end this video now. We're going to finish up the chapter in the next video, and it won't be quite as long.